As we mentioned previously, that the continuous function f(x) in between the interested interval a to b satisfy the boundary condition can be represented by any unique function which is constructed by the eigenfunctions based on orthogonal properties. Then we go back to that topic. What is orthogonal properties? Okay, the orthogonal of eigenvectors, means we have, for example, ym, yn will be equals to, for our problem set, we have our yn will be equals to n pi over L sine x, right? So we have our previous, the SL problem generate the eigenfunctions, which is sine n pi over Lx. And because that is a SL problem, and as we say that the properties of SL problem is that the generated eigenfunctions has to be orthogonal, then let's use this as an example to prove our orthogonal properties. So ym, yn will be equals to from 0 to L. That is the interest interval we are getting from the boundary conditions. Ym x, yn x, that is the inner product of yn, ym, which also over the weight x dx. That will be equals to 0 to L. Ym will be sine m pi over L x. Ynx will be n pi over L x sine omega x in our problem set, which is minus y double prime equals to lambda y. So that was our problem. The omega will be 1 for this case. So it will be 1 dx. Omega x equals to 1. So we have the inner product of ym, yn will be equals to this integral. And we also know that the sine phi will be equals to half of cosine theta minus phi minus cosine theta plus phi. Okay? And we have our inner product ym, yn, then that will be equals to half, okay? Half of from 0 to L, cosine theta will be m minus n pi over L x minus cosine m plus n pi over Lx. So we just use this format to represent a product of two sine functions, okay? Then when our m is now equals to n, okay? When m is now equals to n, this inner product ym, yn will be equals to 0, because think about this cosine function and the second cosine function. These two cosine function, the frequency is only difference by 2n. Then when you differentiate by 2n, then basically this value will be equals to that value. And when they subtract to each other, will be equals to 0. Okay? Simply, you can also try different m and n to validate this result. When you m equals to n, what we have? So m equals to n, this part will be 0, cosine 0 will be equals to 1. Okay. When you have m equals to n, that will be 2 cosine 2n pi over Lx, and that part will be equals to 0. So the inner product ym, yn will be equals to half from 0 to L, cosine 0 will be 1, dx, okay, this is dx, will be equals to L over 2. So L over 2. Then you also know that this is basically equals to yn square root. And that means yn magnitude will be root of L over 2. L over 2. And what we can get is you can write basically what is your Fourier series to represent your smooth function of fx. So the Fourier series means any function fx which is continuous and smooth in between your boundary condition, which is 0 to L, and satisfy the boundary conditions, which is for our problem set is y0 equals to 0, yl equals to 0, f0 equals to 0, fl equals to 0, can be written uniquely as fx equals the sum n from 1 to infinity, okay, n from 1 to infinity, cn sine m pi x over L, okay, m pi x over L, that is uyn. This is the coefficient, where the coefficient cn will be equals to f sine n pi x over L, right? So f yn over yn, right? So yn is sine n pi x over L, sine n pi x over L. And that is basically yn squared, which is L over 2. So divided by L over 2 will be times 2 over L. The inner product of f sine n pi x over L. Okay. So that is how you can present different smooth function fx using Fourier series. And we will make several examples next week.